Hello, good afternoon. Am I audible to you?
Yes, sir.
Okay, screen is visible?
Yes, sir.
All right, so in the last lecture, avionics, we were solving the numerical based on the proportional navigation guidance systems and APN. So we use this numerical, and for proportional navigation, we have solved the numerical. That was your question number 2. What was the question here? That consider the missile target engagement geometry is given below for a instant time t, and we need to answer the following question. We need to find the latex command if the missile is using Pn with n is equal to 4, that is your navigation guidance constant, and we got the latex command value. Now similarly for APN, we want to find out the latex command with n is equal to 1, sorry, n is equal to 3. So what is the difference between PN and APN? In APN, what we are considering is the maneuverability of the missile target. That means your y separation velocity and separation acceleration, that is y dot and y double dot, will not be 0. There will be some non-zero value for separation velocity and the separation acceleration. Now here in the diagram, the velocity of the target is given at some particular angle 120 degree. Acceleration is given 20 meter per second square at some particular angle. So we want to find out the latex required for the APN. So can you try? It is similar to the previous questions, only we are changing the guidance law from PN to APN. So what is your guidance law for APN? For APN, that is this is your guidance command, that is AM is equal to n divided by time to go square into y plus y dot into time to go. It was similar in the previous one, only n is changing, plus 1/2 ATN into t raised to square. So we need to find out ATN. If you can find out ATN, then you can simply add it in the previous answer, and that will be your latex command. Now what is ATN? ATN is the vertical. Hello.
Sir, this AM formula has been derived, no?
Yes, this formula is derived, right? We have already derived this formula from the APN and APN. Like here we have derived it. First we derived for PN, then we added the APN. So we are using this formula. Okay. Now what is ATN is the target acceleration normal to the LOS. Now what is your LOS here? LOS, and the acceleration direction is given, but it is not normal to the LOS. We need to find out the normal to the LOS. How we will find out it? Now what will be the angle here? Angle is not given. We need to assume the angle. I think it is a rectangle to the velocity vector. If you look at the geometry, the acceleration vector is the at 90 degree of velocity vector. So velocity vector is given 120 degree from the ground. So this will be 120 minus 90, so it will 30 degree. So from that we can find out, but that is will be 30 degree with respect to horizon. We want to find out latex. So AN will be the perpendicular to your line of sight. Line of sight is 15 degree. If you draw the 15 degree line here, if you draw the 15 degree line, suppose this is the line of sight. Now angle between line of sight and this will be this one. So total angle was this angle was 30 degree. How we got this 30 degree? Total is 120 and velocity and acceleration are at 90 degree. So 90 minus 120 minus 90 will become 30 degree. Now from horizon and the line of sight is 15 degree. So remaining this angle will become 15 degree. So for this 15 degree, we need to find out what will be the acceleration. So find out this first of all, the component of acceleration perpendicular to the line of sight, that we need to use in the formula. That will be your y double dot. Y is known to you, y dot is known to you, and remaining components are known to you from the previous numerical. So find out it. It is clear how we derive this or how you come across these angles. Using this angle, we are doing it. Here only what is given is 120 degree. 120 degree angle between horizontal and the velocity vector. And from the diagram, we can see that the angle between acceleration vector and velocity vector of target is 90 degree. Now using this relation, we will find out this angle. Try to solve it now. So this angle is given. This is suppose 30. And if you draw the line here, that is line of sight, will be 15 degree. So this angle will be 15. Now, if you resolve the component here and here. So this is 50. So if you draw this angle will be 50. So how much will be this angle? 50 minus 90. So it will be, find out this angle and resolve the component. I hope you know the trigonometry here. Use the knowledge of the trigonometry and find out what will be the value of A, N, C is equal to Y double dot. Find out. I already have explained it now. Someone please try to resolve the force component or acceleration component for perpendicular direction with respect to line of sight. Angles are given, so it is easy to derive it. So find out normal acceleration or separation acceleration with respect to line of sight, or separation acceleration perpendicular to the line of sight, and tell me the value. See, this kind of numericals will become in the exam, so you need to understand the equations and the geometry so that how you can resolve it and find out the required answer. Someone please solve it, tell me the answer. जल्दी जल्दी, कोई सोल्व कर रहा है?
सर
या
सर वो एक्चुअली लास्ट क्लास में एब्सेंट था, तो आप थोड़ा इसका एएम के उसका वो पूरा फुल फॉर्म का ओवरव्यू दोगे क्या?
कौन सा ओवरव्यू?
मतलब ये जो टर्म आप बोल रहे हो
हाँ,
उसका ओवरव्यू मतलब ऐसे मतलब एक एक लाइन में एक्सप्लेन कर सकते हो क्या?
what is your VM is the velocity of your missile. LOS is the line joining target and the missile. Now VT is the velocity of your target. AT is the acceleration of the target, but it is not given perpendicular to the LOS. It is given at some angle. Okay.
Okay.
So what we want to find out here is
तो APN और सब
yes, sir. Here it is. So what you want, suppose here is your missile and target. Now R will be your line of that is your line of sight and distance of line of sight, and the target separation distance will be Y, and the Y dot will be your target separation velocity, and VT is the velocity of target normal to the line of sight. Similarly, here will be one factor, that is AN, that is the acceleration of the target.
acceleration
Yes.
AM ना?
हेलो.
हाँ सर बोलो.
हाँ बोलो, क्या पूछ रहे थे?
हाँ ये APN.
So in APN, what is the difference? First of all, you need to understand what is the difference between PN and APN.
Okay.
So PN is a proportional navigation guidance law, where we are not using the maneuverability of the target. We are assuming the target is stationary. There is no vertical separation between, or vertical separation velocity between target and the line of sight, and there is no vertical separation acceleration between target and line of sight. Now what is vertical separation? That you can understand from this diagram. Suppose this is the line, or this is the direction of the missile, okay, and VM is the velocity vector of the missile. Now what is the vertical distance between the line, horizontal axis of missile and the target? That is your separation distance Y. Okay. Now we have joined the line target and missile, that is your line of sight, and the line of sight here is R. Now for your PN, for proportional navigation, the velocity Y dot and Y double dot, that is your vertical velocity component of the target, and vertical acceleration component of target is 0. Okay, only we are considering Y. Okay, and using this, your target, matlab, your acceleration part is not comes into picture when you are considering the proportional navigation, and based on that, what we have derived is the equation.
I think acceleration 0 target in proportional navigation.
Okay. आपका आवाज कट रहा है.
अभी आ रहा है सर?
See here, in proportional navigation, what is difference here? Proportional navigation, this Y double dot will be 0. Only we are dealing with the vertical separation distance and the target velocity. We are assuming that there is no maneuveration in the target. If target is maneuvering quickly, then acceleration will comes into picture. Here we are assuming that velocity is constant and acceleration is 0. That is for proportional navigation. And for that we have derived the equation, that is, what is your latest command required will be equal to n into y dot into time to go raised to -1 plus y into time to go raised to -2. That is simply modified as
missile to target, na?
Time to go means what is the time required to hit the target from given time. Okay. Like whatever your current position is, from that position, what is the time required to hit the target? That is your time to go. and final time TF is the time required to hit the target from the starting point. Once you launch the target missile, from that point to the time till you hit the target, that is your final time. And current time is what is your current location, that will be your current time. So time to go will be final time minus your current time will be your time to go. Okay, but it is difficult to estimate, so we have here formula used for estimating the time to go. That is your line of sight distance is equal to closing velocity into time to go. So from here, if your closing velocity and line of sight distance is known to you, we can find out time to go. That's how we calculated in the previous numerical. Now in APN, one more component is added. Yes. In APN, one more component. Sorry.
क्लोजिंग वेलोसिटी मतलब मिसाइल का वेलोसिटी क्या?
हाँ ब्रो.
हेलो सर.
वॉइस कट रहा है तुम्हारा.
अभी आ रहा है सर?
वो क्लोजिंग वेलोसिटी पूछ रहा है.
Closing velocity is relative velocity between missile and target. How if your missile velocity is 0, right? Suppose if your target is stationary, okay. So VT will be 0. In that case, closing velocity will be your VM. Now suppose your target is moving, so there will be relative velocity between your missile and target, right? So that relative velocity will be your closing velocity. So here you need to resolve the component of missile velocity in the direction of your line of sight and component of your target velocity in the direction of line of sight. That is one method. Another method is if the angle is small between your line of sight and the missile current velocity vector, then you can directly take it as a whatever given velocity. That was we have taken in the previous numerical by assuming that velocity angle between your line of sight and the missile is very small. But in actual case, this won't be very small. So we need to consider the component of missile velocity vector in the direction of line of sight. Okay. Similarly, here target velocity will be at some angle. So you need to resolve the component of target velocity in the direction of your LOS. So if you go to the numerical here, if I explain the numerical now. First I explain for this. So here, suppose Vm is given 250 meter per second, right? And the angle between your line of sight and the missile velocity vector is 30 minus 15, so it will be 15. Okay, so 15 is not if it is not a small angle, if you want to consider it is small angle, then Vm will be equal to 250 degree. 250 minus this Vt is 100, so 250 minus 100 will be your closing velocity. Okay, if you are assuming that the angle is very small, that is one method. Here, what is your closing velocity? Simply relative velocity between your missile and target. So 250 minus 100, 150 will be your closing velocity. Now if you apply the angle, second point is if you apply the angle, here angle is 15 degree. Okay, and here what will be the angle? 180 minus 20, it will be 60 degrees. It will be 60 degree here.
60 plus.
Wait, let me tell you. This is 60. This is 60
plus
degree, right?
60 15. 60 plus 15 होगा ना वो?
कौन सा?
वो पूरा 16 है सर.
Yes. This will be your. So we need to range 60 degrees. How much will be this angle? Total angle? 60 plus this angle is between 15 degrees. So it will be 75.
75.
Right.
So it will be Vt 100 into cos 75. Sorry, 250 cos 15 minus 100 cos 75. Right?
Yeah, right. So you need to resolve this velocity of missile for this LOS and velocity of target for this LOS. That was we have not taken this in the previous numerical. But once your this theta is larger, we need to take it into consider. So here what will be your closing velocity? The component of missile velocity in the LOS minus component of target velocity in the LOS. So that will be your closing velocity. Now it is clear?
Yes, sir.
Okay, so now you can solve this numerical. Somebody please try now. First of all, find out the ATN. Only you need to resolve this component of acceleration in the direction of normal to the LOS. So here angle we already described. So based on this angle, you can try and find out the vertical component of acceleration or component of acceleration normal to the line of sight and tell me the value. Find out A and T. This will be really confusing if you're not solving now. जल्दी करो, कोई तो solve करो.
Sir, A and T will be 20 sine 15, right?
Cos. Yeah. Sorry.
Hello.
Yes, it is 29.15.
So
So here it is given, right? So this will be the
that is showing 5.17.
5.17. Okay, so this will be a 5.17 meter per second square. This will be your y double dot. Now next we need to find out y dot. ये कितना होगा? Velocity normal to the LOS. Find out. Similar method into find out velocity normal to the LOS. Find out y dot.
$86.6.
86.6. Okay, now n is given to you. We will directly use it in the formula of your APN. That is, here it is the formula. N divided by time to go square into y plus y dot time to go plus 1/2 ATN time to go square. ATN is already you have calculated. Y dot you calculated. Y is given. So you will get the required LaTeX command for the missile using APN. Find out कितना आ रहा है?
सर वो ZEM क्या बोला?
ZEM is zero. क्या बोलते हैं? एक मिनट. Zero effort miss. That is a miss distance. If you consider the diagram, this is the distance by which your missile will miss the target. So this will be termed as zero effect miss. Means if you are not applying any effort to your missile, or if you are not applying any LaTeX command to the missile, then this will be your miss distance between your missile and the target. So this is known as zero effort miss, ZEM. Similarly for APN, ZEM will be this one.
वो डिस्टेंस ही है ना?
Sorry?
डिस्टेंस है ना वो?
That is your distance. Means this is how much distance your missile will miss the target.
LOS की है फिर वर्टिकल डिस्टेंस?
You are talking about which?
So miss distance. Distance is not having direction.
क्या?
Distance is a scalar quantity. It doesn't have a direction.
डायरेक्शन में बोल रहा हूँ मैं. हम talking about
What is your question, Sushil? What is your question?
ये आपने बोला it is the distance between the missile and the target
Yes.
before hitting. तो वो distance
Okay.
मतलब
Let me go back to the diagram. Okay, then you will be understanding it.
okay sir.
Suppose this is your missile direction. Okay, this dark line is the missile direction. All right, it is heading towards the this is your missile direction. Okay, and this is your target position, right? Now, if you're not applying if you have to keep the missile in this direction, this is the actual trajectory of the missile if you want to hit the target, right? Now, if you are not applying any latex command, means missile will be traveling in this direction and it will be missing the target. So this will be the distance it will miss. Okay. So that will be the distance, or that is the miss distance in the case if you are not applying any latex command. So ZDM is nothing but zero effort means if you are not applying any effort to the missile, that will be your miss distance. That is why term is given zero effort means miss distance. Clear now, Vilis?
Yes, sir.
Okay. So now it is clear what is difference between PN and APN.
Yes, sir.
Okay. Now one more term is missing here is we are not considering the time delay and the error involved in the measurement or error due to the atmosphere and all. So if you want to apply the time delay that is faced by the autopilot system, because we know autopilot system is control system, and you already studied what is the time delay in first order and second order system, right? Time delay time, rise time, peak time. You already studied it in the control system. Have you studied or not? Hello.
Yes, sir.
Okay. So what is delay time? It is time required to reach the signal at 50% strength of the maximum strength. That will be delay time. Similarly, you have peak time, rise time, and here if your missile control system is generally the first order control system, not the second order control system. In first order control system, what will your time delay? If you want to consider the time delay that is taken by the control system, then we need to follow the modern guidance scheme that is derived using the optimal control theory, and that is considering the time delay by the autopilot. So that is another system, another guidance law, that is your modern guidance scheme. Clear between APN and modern guidance scheme? APN is not considering the time delay by the autopilot system, but your modern guidance scheme is considering the time delay by the autopilot system. So it is very difficult to measure and maintain, but still we can derive it for modern guidance scheme. न्यूमेरिकल सबको क्लियर है यहाँ तक?
Yes, sir.
Okay. So here in this numerical, if you compare, first let me finish this. The command latex for PN and APN, you got the value of command latex for PN and APN, and if you observe the APN latex command, value will be high initially, but in the terminal phase, the latex command value will be less, whereas in the PN, the latex command value will be low in the beginning, but in the terminal phase, it will be high. So now we'll go back to the MGS, that is your modern guidance scheme. In modern guidance scheme, we are considering the time delay that was faced by the autopilot or your lateral autopilot system. Using the optimal control theory, we are deriving the relation for it. And here what we are assuming or we are considering is what is the drag or induced drag the missile will be facing due to the maneuvering. As you apply the latex command, the control surface will change and the direction of your missile will change. So due to this maneuvering, there will be some induced drag that will be affecting the velocity of your missile, and using this drag, and we want to minimize this induced drag. For that we will be designing the MGS. So we are considering the induced drag that was produced by the maneuvering effect, and we want to keep it minimum in the MGS. So for this, we are integrating the latex command of the missile with respect to final time 0 to F, means throughout your journey of your missile or throughout your mission, we are integrating the latex command, because at one particular point throughout the time, suppose if you go back to the numerical, this is your line of sight. Okay, now at this point, at this point, at this point, at this point, the requirement of latex command will be different, right? So as your latex command requirement will be different, the drag produced by this latex command or by this maneuvering will be different. So if you integrate the latex command throughout this time 0 to time f, from beginning to the terminal phase, or from beginning or launch to the hit of the target, then you can get the requirement of induced drag and what is the minimum induced drag will be produced by this maneuvering. So here, to keep the minimize or to design the MGS in such a way that minimize the following term. So this term we are minimizing in so that your induced drag will be low. So here if you integrate your latex command from 0 to TF and to keep it minimum under the condition that terminal guidance is, or sorry, miss distance is 0, means you are not missing the target, but you want to minimize this value in order to minimize the induced drag. So this is one condition for designing your MGS, modern guidance scheme, that your overall what you call latex command will be minimum by from 0 to TF. Suppose at time 0 latex command will be high, at time 1 it will be high, but it will reduce, it will go nearby. So overall will be minimum, so that your maneuvering drag will be minimum, and condition that terminal miss distance is 0. You are keeping the induced drag and the latex command minimum, but you are not missing the target. That is the condition to design modern guidance scheme. So this is a formula, or this is the, you need to integrate, or integration of latex command from 0 to TF should be minimum. This is one condition. So for linearized geometry and small augmentation angle, means your y at TF will be 0, means miss distance at terminal phase is 0. And by solving this using optimal control theory, we are deriving this guidance law. We are not going into derivation because it will be requiring the modern control system knowledge, as we are not expert in modern control system, as you only studied the basic control system, and optimal control system again you have not studied. So we are not going to optimal control theory to derive this relation, but this relation is for modern guidance scheme design. Only the condition is this term will be minimum and miss distance will be minimum. So here this is one condition and this is another condition, that y at TF, that is your miss distance is 0, and your overall vertical latex command or overall latex command is minimum for minimum maneuvering drag. So this is your minimum value and this is 0 value. And using these two conditions, we have derived the requirement or required vertical latex command for missile is equal to n dash divided by time to go square. What is n here? N is the guidance constant, but in the proportional navigation and APN, guidance constant was constant, but here the guidance number is not constant. It is vary with respect to time and velocity. So that is why the symbol is taken n dash. It will not be constant, it will be variable. Time to go square into y plus y into time to go, and system was again 1/2 APN square time to go square. So if you remember, this is the terms we used in APN, right? And this is two terms we used in proportional navigation. So first we derived for proportional navigation, then we added this term for maneuvering. Now we are adding this term for the consideration of your autopilot delay time. So we are adding this term minus AM into under bracket e raised to minus t plus t minus 1 divided by omega square. Omega is the bandwidth of your autopilot system and t is the time that is one that time domain constant, that is e raised to s and e raised to t we are considering, right? So this is your time domain analysis. So for that e raised to minus t plus t minus 1 divided by omega square, and am is the what is the vertical acceleration of your target, sorry, missile. So here this is currently what is your available acceleration of the missile and what is the required acceleration of the missile. So you need to subtract the current acceleration, multiply by with the systems to consider the time delay of your autopilot system. So that will give you the required latex signal for the given condition. It is clear how we get this equation from your proportional navigation and APN. We are adding the time delay using optimal control theory. This is derived from optical control theory, and we subtracted from APN to get the required latex command for modern guidance scheme. This is clear? Hello. Now, one by one, we go for the terms. What is time? So this term T is equal to omega into time to go, where omega is the bandwidth of the guidance system. So we need to first calculate the bandwidth of the guidance system from given time delay. How we can consider? Yeah. The formula is omega is equal to 1 by tau. Tau is the time constant for the first order system. What is the first order system time constant tau? And that is depending on the delay time. So this term will be depending on the delay time. Again, so bandwidth will be depending on the delay time. So your term T, capital T, will be depending on delay time. So this entire term will be depending on delay time. And similarly, your latex command will be depending on delay time, or that is dynamics of your control system. So here your missile control system or missile autopilot system is taken into consideration, and we are assuming this is your first order control system, and the network is time lag network. There may be time lead network or lead lag network, but as we are talking about the delay time, so it will be time lag network. And for time lag network, what is relation between delay time and the time constant, that kept small t, that is delay time multiplied by the time constant, is equal to 5. Using this, we will be calculating the bandwidth, and from bandwidth we consider the time t, capital T, and we find out the latex command. Now, if you consider here value of n, which was not constant as it was in case of APN and PN. So you need to find out first n dash. Okay, wait, let me erase this. So here, how you will calculate the value of your guidance number is equal to 6 t square into e raised to minus t minus 1 plus t divided by 2 t raised to 3 plus 3, 6t minus 6t square minus 12 t into e raised to capital T minus t. This is a big formula we need to consider while designing the guidance scheme. That is a modern guidance scheme. Means you need to first calculate the guidance number. Earlier it was constant, but as it is autopilot, delay time comes into picture. The guidance number will be variable. It will depending on the bandwidth and the delay time. So, and again, delay time will be depending on the maneuverability of the target. So this will not remain constant. Now, if you take delay time equal to 0, or